Imagine for a moment you're building this magnificent skyscraper. Huge project.
Okay.
You've got teams from all over sending you pieces, steel girders, glass panes, wiring, you name it.
Right, the components.
But then you realize every single supplier, they use a completely different set of instructions.
Oh, boy.
The girders come with metric plans, the glass uses imperial, and the wiring, well, it's in some proprietary language only they understand.
That sounds like chaos.
Exactly. The chaos, the rework, the astronomical costs. That's pretty much what the world of electronics design used to be like.
It's a really good analogy, actually.
Yeah.
Because that chaos, it directly mirrors the challenges we faced with integrated circuits, ICs, and systems on chips, OCs.
The brains inside everything.
Pretty much everything,
Oh.
yeah. The tiny brains. And making sure these incredibly complex designs work perfectly before you physically manufacture them, that's, well, one of the biggest, most expensive challenges in tech.
Catching a bug late must be painful.
Oh, incredibly painful. Catch a single bug too late, you're looking at potentially millions in losses, mask respins, delays. It's bad news.
And that's where today's deep dive comes in. We're peeling back the layers on something called the Universal Verification Methodology, UVM. Our mission today is really to unpack how UVM emerged as the industry standard that, tamed this complexity, saved companies huge amounts of money, and why it now underpins almost every new chip design you see.
It really does.
So you'll walk away understanding not just what UVM is, but why it's so critical, and maybe even where it's headed next.
Yeah, the exciting future stuff, too.
Okay, so let's rewind a bit. Back to the early 2000s, chip designs were just exploding in complexity, right?
Absolutely skyrocketing. Moore's Law was in full swing.
And the old ways of checking them, verifying them, just weren't cutting it anymore.
Not at all. They were hitting a wall.
Which led to what people in the industry actually called the methodology wars. Sounds dramatic.
It kind of was. Picture this. You had these powerful but totally incompatible verification methods popping up from the different EDA vendors. Electronic design automation companies.
Right.
You had things like ERM from Vericity, VMM from Synopsys, AVM from Cadence. Each was good on its own, sure, but they just didn't talk to each other at all.
And that created a massive bottleneck, I imagine, especially for reusing design.
Oh, a huge bottleneck for intellectual property or IP reuse. That was the real pain point.
IP blocks being those pre-designed chunks, like a Wi-Fi controller or something.
Exactly. Pre-designed, pre-verified chunks of circuitry you want to just drop into your new chip. Saves a ton of time.
But if one block was verified with, say, VMM, and your main chip design used AVM...
You were stuck, pretty much. You had to spend a lot of time, a lot of money, creating these wrappers to translate between them, or worse, completely re-verifying that IP block from scratch.
Which defeats the purpose of reuse.
Totally defeats the purpose. It severely hampered efficiency. It was like, buying this brilliant engine, but it only fits one specific car model from a rival maker. Useless.
So the industry was crying out for a solution, something unified?
Desperately. The first real step towards that unification came in 2007. That was the Open Verification Methodology, OVM.
Okay, OVM.
It was a joint effort. Cadence and Mentor Graphics got together. They provided this robust, open-source methodology based on system Verilog. It merged ideas from their own older methods.
And did it catch on?
It gained a lot of traction, yeah. It offered a glimpse of, more unified future, a possibility.
But it wasn't the whole solution yet.
Not quite. The ecosystem was still fractured. Synopsys' VMM still had a huge user base, you see. The real push, the pressure for a single universal standard actually came from the big semiconductor companies themselves.
The chip makers.
Yeah, the Intels, the Qualcomms, the NVIDIAs of the world. They were the ones really burdened by the cost and the risk of integrating IP across all these different verification flows.
They must have been losing millions.
Oh, absolutely. So they essentially went to the EDA industry and said, look, give us one standard or we'll make one ourselves.
Wow, okay. Strong message.
Very strong. And that pressure led the standards organization, Accelera, to form a technical subcommittee. That was December 2009.
And they delivered.
They did. UVM 1.0 was approved and released in February 2011. Crucially, it was directly based on OVM 2.1.1.
So it built on that earlier effort.
Exactly. And that was basically the peace treaty. It effectively ended those methodology wars.
And the significance of this wasn't just practical, it became official.
That's a key point. UVM didn't just become the default standard everyone used. It became an official IE standard,
Yeah.
IEEE 200.2.
Putting it on par with System Verilog itself.
Precisely. System Verilog is the language, UVM is the methodology standard that uses it. This cemented its role. And Accelera even sponsors the IEE GET program, which means engineers can get free access to the official standard documents. That really helped adoption.
And it's kept evolving since then.
Oh, yes. It's not static. It's seen updates, like IEE 1800.2 2017 and then 1800.2 2020. Always refining, improving consistency, reliability.
So UVM isn't just a library of code you download. It sounds much more like a fundamental shift in thinking, a philosophy for verification engineers.
You've hit the nail on the head. It is a philosophy, and it's built on core principles. Probably the most important one is modularity and reusability.
Okay, break that down. How does that work in practice?
Think of a UVM agent. It's like a self-contained package pre-tested for verifying a specific design interface, like, say, an AXI bus interface or I2C or something common.
Right.
This agent isn't just cleaner code. It means that component, developed once, can be trusted. And you can instantly plug it into any new project using that same interface.
So you build it once, use it many times.
Exactly. You can reuse it horizontally across different projects and also vertically, taking the same agent you used to test a small block and plugging it into the verification environment for the whole chip.
That sounds incredibly powerful, must save enormous amounts of effort.
It's a true engineering superpower. It slashes redundant effort and really accelerates development schedules.
And that modularity, that must help with scalability too, because chips just keep getting bigger and bigger.
Directly ties into it. UVM test benches are built hierarchically. Think of them like nested Lego blocks.
Okay.
You have a top-level environment, usually called a UVM FD. That environment can contain multiple agents, maybe a scoreboard for checking, maybe other environments nested inside it.
You can build up complexity.
Seamlessly. This structure scales really well, letting you go from verifying a tiny little IP block up to a massive multi-billion transistor system on chip without having to constantly start over from scratch.
Okay, so it's modular, it's scalable, but how do you actually use it to find the bugs? It sounds more sophisticated than just writing a few tests by hand.
Way more sophisticated. That brings us to the core verification strategy. Constrained random, coverage-driven verification. CDV.
Constrained random, coverage-driven.
No. Yeah, this is the modern paradigm. We move beyond just manually writing specific directed tests for every little thing. That just doesn't scale for complex chips.
So what does constrained random mean? Is it just throwing random data at the chip?
Not quite random chaos. It's smart random. UVM helps you automatically generate a vast number, potentially billions, of test stimuli inputs for your design. But they're constrained to be legal or perhaps strategically illegal according to the design's rules.
Ah, so it explores possibilities but within boundaries.
Exactly. Think of it like a highly intelligent storm generator. It can create everything from a gentle drizzle to a Category 5 hurricane, but it always obeys the laws of physics. It generates interesting, valid, and sometimes stressful scenarios automatically.
Okay, so you generate this massive, smart storm of stimuli. How do you know if that storm actually hit all the important parts of your design? Did it test the tricky corners?
Excellent question. That's where the second part comes in. Functional coverage.
Coverage. Measuring what you've tested.
Precisely. Functional coverage measures the effectiveness of all that random stimulus. It tracks whether specific design features, critical operating modes, tricky corner cases, protocol rules, whatever you define as important, have actually been exercised by the test.
So it's like having a checklist that gets automatically ticked off as the random tests run.
Kind of, yeah. And the ultimate goal is coverage closure. You keep running regressions, automated batches of these constrained random tests, analyzing the coverage results, maybe tweaking constraints or adding specific tests to hit the gaps, until those coverage metrics reach your target, say 100%.
So you have confidence you've thoroughly exercised the design.
Much higher confidence than just running a few handwritten tests, yes. It tells you, okay, we've actively tried to hit all these known important scenarios and features.
And there's one more key principle you mentioned about architecture.
Right. A really fundamental architectural principle in UVM is the separation of tests from the test bench.
What does that mean?
It means the test bench itself, the structure with the environments, agents, monitors, drivers, scoreboard, is relatively static. It's like your fixed test apparatus, your hardware rig.
Okay.
The actual tests, the specific scenarios you want to run, like send a burst of data, then cause an error, are implemented as dynamic objects, usually event sequence objects. They get created and run on the static test bench.
So the test bench stays stable and you just swap different test sequences in and out.
Exactly. This decoupling is incredibly powerful. It allows an almost infinite variety of test scenarios to be developed and run on the same, stable, verified environment without constantly modifying the underlying test bench components.
That sounds like a huge boost for reusability again.
Massive. It's like having one reliable, well-calibrated car and an endless supply of different road trip plans you can use with it.
Okay, so bringing it all together, UVM's core purpose is basically finding those nasty bugs before they become incredibly expensive silicon problems.
That's the heart of it. Its primary application is pre-silicon functional verification. You build these comprehensive test environments to rigorously stimulate the design, under-test the DUT, that's the actual chip logic, check its responses, and identify bugs before you commit to the costly process of silicon fabrication.
Let's talk some real-world examples. Verifying something like a modern processor, that sounds like a complete nightmare. All those pipelines and hazards.
Oh, it absolutely is a nightmare without a methodology like UVM. Processors have deep instruction pipelines, complex data dependencies, control hazards, things like branches, exceptions, interrupts. It's incredibly intricate.
And you have to make sure the final state, the registers, the memory is exactly correct after every instruction.
Exactly. Ensuring the integrity of that architectural state is paramount. So in UVM, you typically have an agent acting as an instruction generator.
Feeding instructions into the processor model.
Right. It feeds instruction objects, which are UVM sequence items, to the processor's fetch interface. And the stimulus is often a hybrid.
Hybrid, meaning random and directed.
Yeah. You use broad constrained random tests to explore the general behavior, find unexpected interactions, but you also use highly directed sequences to specifically target known difficult corner cases, maybe complex hazard scenarios or specific exception sequences that pure random might take forever to hit.
And how do you check if the processor did the right thing?
That's where a golden reference model comes in. It's often an instruction set simulator, or ISS, maybe a C model of the processor. It executes the exact same instruction stream that you fed to the DUT.
Okay.
Then, your UVM scoreboard compares the final architectural state, the registers, relevant memory locations from the DUT against the state from the golden model. Any mismatch is a bug.
Makes sense. What about something different, like high-speed networking chips? Or those really complex cache-coherent interconnects? Managing data flow and consistency there must be tough.
Very tough. That's where UVM's hierarchical and reusable nature really shines again. Think about verifying a big networking ASIC, like an Ethernet switch.
Lots of ports, complex protocols.
Exactly. Layered protocols, high-speed data flow, ensuring data integrity across multiple ports simultaneously. Or consider cache-coherent interconnects, maybe using AMBA, XIACE, which is a common standard.
That's for making sure multiple processors see the same view of memory.
Right. Ensuring data consistency when multiple masters are accessing shared memory. The complexity there is monumental. You have snoops, cache states. It's tricky.
So how does UVM handle that complexity? Multiple ports? Coherency rules?
The UVM architecture maps beautifully. For that multi-port switch, your test bench would likely instantiate multiple UVM agents, one VIP agent for each protocol interface, like Ethernet or PCIe.
Okay, an agent per port.
Pretty much. And to coordinate behavior across them, you use what's called a virtual sequence.
Virtual sequence.
Yeah, it's a higher-level sequence that doesn't generate transactions itself. Instead, it orchestrates subsequences running on the individual physical agents. It's like a conductor telling the different sections of the orchestra when to play.
So you can create complex, system-wide traffic scenarios.
Precisely. Sending packets in one port while monitoring another, simulating congestion, testing quality of service, etc., and for cache coherency. Your environment would have agents for each master interface, plus a sophisticated system-level scoreboard.
What does the scoreboard track there?
It tracks the expected cache states across the entire system, monitors bus traffic, checks that the interconnect initiates the right Snoop transactions when needed, and basically verifies that the coherency protocol rules are being followed correctly. It's complex checking.
And UVM seems pretty adaptable, too. You hear about it being used in areas like low-power design or even mixed signal verification now.
Absolutely. It shows the flexibility of the methodology. For low-power designs, the big challenge is verifying all those power-saving features, power gating, clock gating, dynamic voltage, and frequency scaling, DVFS.
Making sure turning parts of the chip off and on doesn't break things.
Exactly. Making sure you don't corrupt data or mess up functionality during those power state transitions. So, UVM test benches get integrated with a power intent specification, usually written in the Unified Power Format, UPF. Okay.
Your UVM sequences then actively trigger power state changes, and you use special power-aware assertions and coverage points to check things like isolation logic working correctly or state retention registers holding their values.
And mixed signal, combining analog and digital. That seems like a huge hurdle, bringing continuous values into a digital framework.
It's traditionally very difficult, yeah. Digital methods like UVM weren't designed to handle continuous time analog signals easily. But the newer UVM-MS, mixed signal standard, tackles this.
How does UVM-MS work?
Its key component is the MS bridge. It's essentially a special system Verilog module that acts as a translator. It converts digital transaction-level data from the UVM world into continuous real number values that the analog simulator understands, and vice versa.
Ah, a bridge between the two domains.
Exactly. This allows UVM's powerful stimulus generation, its sequence capabilities, its checking infrastructure like scoreboards, to be applied effectively to analog behaviors too. You can have reusable UVM MS VIP now. It's a real game changer for verifying modern SOCs that blend analog and digital heavily. So UVM is this powerful methodology, this philosophy, but it doesn't exist in a vacuum. It really comes to life through an ecosystem of sophisticated software tools, right? The EDA tools.
Absolutely. You need a whole tool chain. And these tools need to be UVM aware to really unlock the benefits.
What does that tool chain typically include?
Well, first you need the simulators. High-performance engines that compile your system Verilog RTL code, the chip design itself, and the UVM test bench code, and then simulate their interaction over time.
Okay, the core simulation engine.
Then you need advanced debuggers. And just looking at waveforms isn't enough for UVM. You need UVM-aware debuggers.
And it makes them UVM aware.
They provide specialized views. They let you navigate the UVM test bench hierarchy, easily see the environments, agents, components. They let you trace transactions as they flow from a sequence down to the driver pins. You can visualize UVM class objects and their properties. It goes way beyond just raw signals.
Helps you understand what the test bench is actually doing.
Exactly. It makes debugging much faster. Then you often have test bench and component generators, tools that automate writing some of the boilerplate UVM code.
Speeding up development.
Right. They might take a higher-level description, maybe in a format like IPXACT, which describes IP blocks, and generate the basic UVM agent structure for you. And finally, increasingly important, are formal verification tools.
We touched on formal briefly. How does it fit with UVM?
They're complementary. Formal tools use mathematical algorithms to prove certain properties about the design, or find bugs simulation might miss. They don't replace UVM simulation, but they augment it, especially for control logic and finding really tricky corner cases.
So who are the main providers of these UVM toolchains, the big three EDA vendors?
Yes, Synopsys, Cadence, and Siemens EDA really dominate this market.
What are their key offerings?
Synopsys has VCS as its simulator, known for high performance, and their Verdi debugger is, well, pretty much the de facto industry standard for debug visualization. They also have a huge library of verification IP, VIP, and automation tools.
Okay.
Cadence pushes multi-core simulation performance with their Excellium simulator. And their big differentiator lately is the Vrisium AI-driven verification platform. They're heavily investing in using AI and machine learning for things like automated root cause analysis during debug. Tools like WaveMiner.
Interesting. Using AI to speed up finding bugs.
Exactly. And Siemens ED, who used to be Mentor Graphics, they offer the Questa Advanced Simulator and the Visualizer debug environment. They've also historically put a strong emphasis on methodology and education. Think of the Verification Academy online, the UVM cookbook, and they have their own framework, UVMF, to help structure UVM development.
Are there other significant players too?
Definitely. Aldec, with their Riviera PRO tool, has a solid presence, especially in the FPGA verification space. They offer a full UVM suite, and even FPGA vendors themselves, like AMD with its Vivado simulator, now include robust UVM support. That's really bringing advanced verification to the complex programmable logic world.
So the clear trend isn't just selling individual tools anymore, but these integrated platforms. And AML seems to be the new frontier for competition.
Absolutely. It's all about integrated verification platforms now. Productivity, automation, that's the name of the game. And AML is seen as the key enabler for the next wave of productivity gains, automating the really labor-intensive parts like debugging complex failures or achieving coverage closure faster.
Okay, we've covered the why UVM exists, the what it is, and the tools. Let's dive into the how. If you're an engineer actually building a UVM test bench, what's the typical architecture? You said it's not monolithic?
Definitely not. Think hierarchy. Think interconnected class-based components, like building with specialized Lego bricks, as we said.
Right.
The UVM library itself makes a fundamental distinction. You have your UVM component-derived classes. These are the static structural parts of your test bench. Things like environments, agents, drivers, monitors. They exist throughout the simulation.
The persistent building blocks.
Exactly. And then you have object-derived classes. These are more lightweight, dynamic data objects. Things like the transactions being passed around or configuration objects. They get created and destroyed as needed.
Okay, components are static structure, objects are dynamic data. So what are the canonical components, the standard building blocks everyone uses?
At the very top, you have the OVN test. This is the component that controls each specific simulation run. It instantiates the main environment, configures it for that particular test, and kicks off the master sequence that generates the stimulus.
So each test run has its own OVN test.
Usually, yes. Inside the test, you typically have a OVN. This is the main container for your verification components. It might instantiate several agents, a scoreboard, maybe a reference model, maybe other nested environments.
And environments can be nested.
Oh yeah, that's key for reuse. You might have a block-level environment that you then instantiate inside a subsystem-level environment.
And inside the environment, you have the agents we talked about earlier.
Right. The UVM agent is that fundamental unit of reuse for a single interface protocol. And remember, it has those two modes.
Active and passive.
Exactly. UVM active mode means it drives stimulus via its driver and sequencer, and it also monitors the interface. UVM passive mode means it only observes via its monitor for checking or coverage collection. That passive mode is crucial when you reuse an agent inside a larger system test bench.
Makes sense. So drilling down further, what are the core pieces inside an agent or maybe sitting alongside it in the environment? What do they actually do?
Okay, you have the UVM driver. Its job is to receive those abstract transaction objects from the sequencer.
The sequencetums.
Right, and it translates them into the actual pinwiggles, the signal activity that the DUT understands. It drives the physical interface.
Okay, abstract to physical.
Then you have the UV monitor. It does the opposite. It watches the physical pin activity on the interface, reconstructs the abstract transaction objects from those signals, and then broadcasts these observed transactions to anyone interested, like the scoreboard.
Physical back to abstract.
Exactly. Then there's the UVM sequencer. Think of it as the traffic manager for stimulus. Sequences send transaction requests to the sequencer, and the sequencer then forwards them, one by one, to the driver when the driver is ready. It manages the flow of stimulus generation.
Got it. Driver, monitor, sequencer, and the checker.
That's typically the UVM scoreboard. It's the primary checking component. It usually receives transactions from monitors, representing actual DUT output, and compares them against expected transactions, which might come from a reference model or be predicted based on inputs. It reports any mismatches as errors.
Okay, so those are the main players. How do they communicate? You have drivers talking to sequencers, monitors talking to scoreboards. How do they pass those transaction objects around without creating a tangled mess?
Through transaction-level modeling interfaces, or TLM.
TLM.
Yeah. UVM provides standardized TLM ports, exports, and IMPS implementations. These allow components to connect and communicate simply by passing those UVM object transactions between them. It abstracts away the low-level details of how the communication actually happens.
Like a standardized plug-and-socket system for verification components.
That's a great way to put it. It's like having a universal USB port system for your UVM components to exchange data packages reliably.
Okay, so once you understand these building blocks and how they connect via TLM, what's the typical workflow? If you're starting a UVM project, what are the steps?
It's generally a structured, iterative process. First step is always verification planning. You need to figure out what exactly needs to be verified, what are the features, the corner cases, the coverage goals.
Define the requirements.
Precisely. Then comes test bench development. This is where you actually build the UVM environment instantiating agents, maybe using pre-built VIP, connecting them, building the scoreboard, the reference model if needed. Code generators can help here.
Building the test rig.
Right. Then, test writing. This involves creating the UVM sequence classes that define the specific stimulus scenarios you want to run. This is where you encode the actual test intent.
Designing the experiments.
Good analogy. After that, it's simulation and debug. You run your tests on the simulator, analyze failures, debug the DUT or the test bench, fix bugs, and iterate. This is often the most time-consuming part.
Finding and fixing the problems.
Yep. And finally, regression and coverage closure. You set up automated regressions to run hundreds or thousands of tests, usually overnight. You collect and merge the functional coverage data from all those runs. You analyze the coverage reports to find holes, areas you haven't tested adequately, And then you refine your tests or constraints to target those holes until you meet your predefined coverage goals.
And then you have high confidence the design is solid.
Much higher confidence, yes. That's the goal.
Now, for engineers who really get into UVM, there must be more advanced techniques, best practices, design patterns that make their test benches even better.
Oh, absolutely. Several common patterns really boost efficiency and maintainability. One big one is the configuration management pattern.
Configuration management?
Yeah. Instead of setting dozens of individual variables to configure, say, a complex agent, like its operating mode, addresses, timing parameters, you create a single dedicated configuration object class for that agent.
Bundling all the settings together.
Exactly. You create one instance of this config object in your test, set all its fields, and then you place this single object into a central UVM database called the UVM config spread. The agent then retrieves this configuration object from the database during startup. It's much cleaner, less error-prone, and often more performant than setting tons of individual configuration values.
Nice. What else?
For coordinating stimulus across multiple agents, especially in system-level environments, the stimulus coordination pattern using virtual sequences is key.
We mentioned virtual sequences earlier.
Right. You have a virtual sequence running on a virtual sequencer. This virtual sequence doesn't talk directly to drivers. Instead, it controls or orchestrates multiple underlying physical sequences, each running on its respective agent sequencer. It's how you manage complex interactions between different interfaces, like starting a DMA transfer on one interface while sending control messages on another.
The conductor leading the orchestra again.
Exactly. And then there's effective register modeling using the UVM register abstraction layer, or RL.
RAL for handling chip registers. That sounds critical for almost any design.
It really is. RAL provides an object-oriented model of all the DUT's memory-mapped registers. You get a class representing your whole register map with objects for each register and field. And
you should generate this automatically, right? Not write it by hand.
Absolutely. Best practice is to auto-generate the RAL model from a specification file, like IPXACT or proprietary formats. Writing it manually is tedious and error-prone.
What makes RAL powerful?
Several things. It provides standardized methods to read and write registers. It supports both front door access, generating real transactions on the DUT bus, and backdoor access, which directly manipulates the register signals in the RTL simulation using simulator commands.
Backdoor access sounds useful for setup or checking quickly.
Very useful for initialization or quickly checking state without waiting for bus cycles. RAL also includes a built-in checking mechanism and a predictor component that tries to mirror the DUT's register values based on observed bus traffic, so your model stays in sync for accurate checking.
Okay, so these patterns help build robust, manageable test benches. But setting up agents for standard protocols like PCIe or USB from scratch still sound like a massive undertaking.
It is a massive undertaking. Months, sometimes years of effort for a complex protocol. And that's where reusable verification IP, or VIP, becomes absolutely essential.
The pre-built, pre-verified components.
Yeah, exactly. These are off-the-shelf, commercially available, UVM-compliant components, usually agents, but sometimes environments or monitors for standard industry protocols. Think PCIe, USB, Ethernet, DDR memory, AMBA buses, you name it.
So instead of building your own complex PCIe agent,
you license a proven, high-quality VIP from a vendor like Synopsys, Cadence, or Siemens. You integrate it into your UVM environment, configure it, and you're ready to go much, much faster.
That must be a huge productivity multiplier.
Immense. VIP allows verification teams to immediately focus on verifying their unique design logic, the stuff that differentiates their product, rather than spending ages reinventing the wheel for standard interfaces. The scalability of a rich VIP ecosystem has been a primary driver, maybe the primary driver, of UVM's widespread adoption.
It makes IP-based design truly practical.
It really does. It de-risks projects significantly. It's like being able to buy that pre-built, thoroughly tested engine for your custom car, knowing it's going to work reliably.
So stepping back a bit, it feels like UVM fundamentally changes when verification happens, this idea of shifting left.
That's a core strategic impact, yes. The shift-left paradigm. It's all about moving testing as early as possible in the development cycle.
Why is that so important?
Because in IC design, the cost of finding and fixing a bug increases exponentially the later you find it. A bug found at the block level, when you're verifying just one small piece of the design, maybe takes a few hours for an engineer to fix.
Okay.
The exact same bug found after the chip is fabricated in silicon. That could cost millions of dollars in mask respins, delayed product launch, maybe even a full product recall if it escapes to the field.
Ouch. Millions versus hours.
It's a staggering difference.
Yeah.
UVM enables this shift left because it makes it practical to do really exhaustive, high-quality verification on individual IP blocks before they get integrated into the larger chip.
Finding the flaws on the blueprint, not when the building's half built.
Exactly that analogy. UVM allows chip companies to find those potentially multi-million-dollar bugs at the earliest, cheapest stage. It fundamentally de-risks the entire design process.
And this ties directly into vertical reuse, doesn't it? Using the same UVM components as you scale up from block to the full system.
Precisely. It's a seamless flow. At the block level, you verify a single IP block, maybe a UART controller or a filter module. Your UVM agent is typically in active mode, driving stimulus to all inputs, thoroughly wringing out that block.
Okay, maximum stimulus at the block level.
Then you move to the subsystem level. You integrate several verified blocks together. Now, you reuse the block-level UVM environments and agents you already built, but the agents connected between those blocks, you might switch them to passive mode.
Just monitoring the internal connections.
Right, they just monitor the block-to-block interactions for checking and coverage. Meanwhile, you might add new active agents to drive the external interfaces of the subsystem. The focus shifts from verifying the block's internal logic to verifying the interactions between the blocks.
Got it. And then finally, the full chip.
At the full chip SoC level, you integrate all the subsystems. Now, most of those reused UVM agents running on internal buses are definitely in passive mode, acting as monitors. The primary stimulus generation often shifts.
Shifts to what?
It might be high-level virtual sequences coordinating system-level scenarios, or increasingly, especially for SoCs with embedded processors, the main stimulus comes from CC++ tests running on an embedded CPU model within the simulation.
For more realistic hardware-software co-verification.
Exactly. You're running actual software code snippets to exercise the hardware, while the passive UVM monitors are still checking that all the underlying hardware protocols and interactions are correct. It provides a very realistic system validation environment.
That makes a lot of sense. But UVM isn't the only verification approach out there. How does it stack up against other methods engineers might use, like just simple directed testing?
Yeah, comparing UVM versus directed testing. For anything beyond the simplest designs, UVM's constrained, random, coverage-driven, self-checking approach is just vastly superior. Directed testing alone is brittle, doesn't scale, and you have no real way of knowing what you haven't tested. For complex designs, UVM is the way to go for functional verification.
Okay. And what about those C-based tests you mentioned for SoC level? Is it UVM or C tests?
It's often UVM and C tests. They have different strengths. UVM excels at deep, hardware-centric verification of IP blocks and subsystems, wiggling every pin according to protocol. C tests running on an embedded CPU model are better at verifying the system from the software perspective, running realistic software flows.
But there's a gap between them.
There is. It's often called the UVM to C gap. It's difficult to easily reuse the verification intent you developed in UVM sequences at the block level when you move to writing C tests at the SoC level. You end up rewriting similar scenarios.
Inefficiency again.
Exactly.
Yeah.
And that's the problem the emerging portable test and stimulus standard PSS is designed to solve.
PSS, how does that help?
PSS allows you to describe your verification intent at a higher, more abstract level, independent of whether it will be executed by UVM or C code. Then, tools can automatically generate both the UVM sequences for block subsystem level and the C tests for SoC level, all from that single abstract PSS model.
Bridging the gap. True reuse from hardware verification through to software tests.
That's the goal. It promises significant productivity gains for full system verification.
And finally, how does UVM compare to formal verification? You said they're complementary.
They absolutely are, not competitors. A strong verification plan uses both. UVM, being simulation-based, is great for verifying complex data path logic algorithms, long sequential scenarios involving lots of state. It's excellent at finding bugs.
But it can't prove there are no bugs.
Right. Simulation can only show the presence of bugs, not their absence. Formal verification, on the other hand, uses mathematical techniques. It exhaustively explores the design state space for specific properties you define.
What's formal good for?
It excels at control-intensive logic. Things like arbiters, complex state machines, protocol controllers. It's fantastic at finding obscure corner case bugs that simulation might take billions of cycles to hit or might miss entirely. And crucially, formal can mathematically prove that certain bad behaviors, like deadlock or data corruption under specific conditions, will never occur or prove that a property always holds.
So UVM for breadth and data paths, formal for depth and control logic proof.
That's a good summary. Use both for maximum confidence.
Okay, so after this deep dive into its origins, principles, applications, and ecosystem, what's next for UVM? Is it reaching the end of its life, or is it still evolving?
It's definitely evolving, absolutely not being replaced anytime soon. UVM's impact has been profound. It standardized verification. It enabled the whole IP-based design revolution for SOCs. It drastically reduced integration risk, and it really professionalized the field of verification engineering. It created a common language and methodology.
So it provides a stable foundation. What are the key future directions built on that foundation?
I think the most significant trend, as we just discussed, is its tighter integration with portable test and stimulus, PSS. Addressing that UVM to C reuse gap is huge for seamless block-to-software-driven SOX flows. That's probably the biggest driver right now.
Making that whole flow smoother. What about AI? We touched on it for tools.
AI and machine learning are going to play an increasingly large role within UVM flows. We're seeing it in tools already, intelligent regression pruning, to run fewer tests, but still achieve coverage closure faster, AI-powered debug for automated root cause analysis. It's about leveraging AML to automate the hard parts and make verification engineers more productive.
Working smarter, not harder.
Exactly. We're also seeing UVM expanding into new related domains. We talked about UVM MS for mixed signal. There's ongoing work and discussion around integrating UVM concepts for hardware security verification, things like tracking information flow, taint propagation analysis, and also for functional safety, ensuring compliance with standards like ISO 26262 for automotive chips, using UVM for fault injection campaigns, and safety mechanism verification.
So UVM's core ideas are proving adaptable to new challenges.
Very much so. Another interesting trend is the democratization through open source.
Making UVM more accessible.
Yeah. As open source simulators add more robust UVM support, it lowers the barrier to entry for smaller companies, startups, and academics who might not afford the expensive commercial licenses. This fosters innovation.
And you mentioned Python earlier. Is that replacing System Verilog for UVM?
Not replacing, but augmenting. There's a definite rise of Python in verification. Frameworks like Cocotab or PuMM allow engineers to write test benches that interact with System Verilog designs, often using UVM-like concepts or even directly interfacing with UVM components, but writing the test stimulus and checking logic in Python.
Why Python?
It attracts engineers who might prefer Python syntax, its huge ecosystem of libraries, and potentially find the learning curve a bit gentler than full System Verilog UVM. It's bringing new people and approaches into the verification space, often working alongside traditional UVM.
So the big picture is, UVM is evolving, integrating with new standards like PSS, leveraging AI, expanding its reach, becoming more accessible. But it remains the stable, standardized core.
Precisely. It's not going anywhere. Its future is about augmentation, enhancement, and integration, building on that incredibly strong, proven foundation that the industry relies on.
Well, there you have it. The universal verification methodology may be the unsung hero enabling these incredibly complex chips that power, well, pretty much everything in our modern world. Born out of necessity, standardized through collaboration, and constantly evolving to meet the next challenge.
And it makes you think, if UVM effectively systematized and standardized the how of hardware verification, tackling that massive complexity, what might be the next big what for the electronics industry? What's the next huge challenge that requires a similar level of standardization, a similarly unified methodology, to truly unlock its potential?
That's definitely something for you to ponder as you go about your day. And if this deep dive has sparked your curiosity, maybe continue your own exploration. Perhaps dive deeper into AI's role in chip design, or look into the fascinating and rapidly growing world of open source hardware development.